is metal, and Aditya is going to present. He is a third-year student at SFU with Professor Shriraman, and his research areas include hardware software code design, compiler optimizations, and domain-specific languages. And he is actively looking for internships. So if anyone is looking, our interns are coming already, so it's a little late. But go ahead.
Very good morning. I'm Aditya Prasanna. I will be presenting our work Metal along with my co-author Anagha, who will be joining us on Zoom today. Our work optimizes indexes. Index data structures are like treasure maps for data retrieval. With the proliferation of sparse data, these structures become crucial for managing and accessing information efficiently. Imagine a library without a catalog. It would be chaotic and time-consuming to find what you need. A common use case for indexes are in storing relational tables in databases, but that's not the only place they're used. They're also used to store and index into abstract data such as social networks in the form of graphs. Hash table indexes are extensively used in creation and indexing of sorted sets. Caching these indexes is a hard problem because of the following three reasons: indirect accesses, a large working set, and an inherent trade-off between reach versus effectiveness while exploiting inter-walk locality. We propose Metal, which introduces a brand new short-circuiting cache design, index cache, which increases index visibility using range tags and exploits key reuse, and a new functional interface called reuse patterns, which leverages inter-walk locality to make the reach versus effectiveness trade-off. With Metal, sparse compute workloads find an effective caching framework. To understand the challenges, let us quickly revisit indexes. Indexes primarily target sparse data. Unlike dense data, sparse data isn't contiguous in memory. Therefore, it needs to be tagged by keys. These keys form the key space upon which an index is constructed. Let's see how an index tree is hoisted on sparse data. Here we have sparse data indexed using keys. In this example, we see that the green nodes batch the key space into ranges. Therefore, we only need to access the bounded range where the search data lies. A node essentially is a collection of keys bounded by a low and high. This batching of key space can be increased by hoisting more nodes across levels, which increases filtering. The fan-out of an index can be set by the application. Here we can see that a new subtree gets added to a given root. This is all well and good, but there are equally pressing challenges when dealing with indexes. In an index, we issue a walk to fetch data identified by a turtle. Due to filtering of the key space across levels, each walk issues a series of indirect accesses to memory, which results in a high walk latency. Realistic workloads issue operators which span multiple walks. This leads to an increased number of accesses to arbitrary memory addresses, resulting in a large working set, increasing the bandwidth. Finally, defining locality in indexes is a hard problem. To explain this, let's assume a cache whose goal is to find the nodes closer to data by not inherently hampering cache utilization. This is easy to ascertain when all the walks are going to the same leaf. Here we see that caching the lowest node, that is highest effectiveness as it is closest to data, is the obvious choice and doesn't hamper cache utilization or reach of the node. In this example, say turtles want to go to different leaves. Here we clearly see the trade-off between reach and effectiveness, which is repeatedly encountered in indexes. We see that caching the green nodes doesn't improve cache utilization as each green node is hit only once. Keeping walk cooperation in mind, caching the common orange node is ideal as it benefits all three walks while also being fairly effective. Those were easy examples. What do we do when there are multiple walks across disjointed regions in an index? How do we make this trade-off dynamically as the walks happen? Sorry. I would now like to hand over the presentation to my co-author Anagha, who will take us through our first contribution, the index cache.
Metal proposes two contributions. The first is the index cache, a novel cache architecture with the index key space exposed to the cache. The second is reuse patterns to enable
I just tested it.
Metal proposes two contributions. The first is the index cache, a novel cache architecture with the Metal proposes two contributions.
Yeah.
Metal proposes
Yeah.
Metal proposes two contributions. The first is the index cache.
I checked that. Yeah, that's actually, it'll mute it. It's 100, right?
No, just below that.
Below that?
System, yeah. Just go there. Press on the right side, those things. Just check
Oh,
that.
okay. Thanks. Decimeter. Oh, okay. Thanks a lot.
Now play, now play.
Yeah. The volume. Shall I try the other?
Yeah.
Space exposed to the cache.
No, this is my own device. Headphone? That was the previous one.
Metal proposes two contributions. The first is the index cache, a novel cache architecture with the index key space exposed to the cache. The second is reuse patterns to Metal proposes two
Just tested it out. Volume now set up here.
Well, this is just the C. Signal. Check. Check. Check 1 2, check 1 2, check 1 2, check 1 2, check 1 2.
Check 1 2, check 1 2, check 1 2. Mic check. Check 1 2, check 1 2, check 1 2. Check, 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 check.
I was thinking about hello. That right?
Metal proposes two contributions. The first is the index cache, a novel cache architecture with the index key space exposed to the cache. The second is reuse patterns to enable Metal to manage the trade-off between index cache's reach and effectiveness and identify interwalk locality. Walks in indexes start from the root since a child's address is only located in the parent. If we had a cache to store and extract intermediate child addresses, we could hypothetically short-circuit the traversal and start from an intermediate node. We could straightaway reduce the walk latency and the working set size, thereby making the cache more utilized and effective. Building a short-circuiting cache is hard, and to understand why, let us look at existing cache designs. Caches generally hold node data tagged by the memory address in order to retrieve it from DRAM, making them operate in the address space. This fundamentally triggers root to leaf walks. To understand root to leaf walks better, let us look at what's in an index node. It consists of a set of keys bound by low and high, and also a set of child pointers. Let's consider a lookup for a key. The walk starts from the blue node, filtering through the keys to find the pointer to chase to the appropriate child node. This blue node is then cached and tagged by its address. As you can see, we were performing the search on the index using a key, that is in the key space, but the address cache operates in the address space. This is an inherent mismatch. Similarly, we search through each node for the key. As we descend down the index, caching touched nodes. We perform such root to leaf walks every time, resulting in thrashing the cache. Let me introduce our first contribution, the short-circuiting index cache. It possesses a unique cache structure that stores entire index nodes tagged by a key range. This key range is extracted from the keys that bound the index node. This new tag design lets it operate in key space, allowing probes to query the cache directly with the search key, thereby allowing short-circuiting. Let us see what a walk looks like with an index cache. Consider an index cache with the following entries. We want to look up key K. We probe the cache before starting the walk by making two comparisons at every entry to check if K lies between the low-high range in the tag. Let us assume that this gray node is unrelated to the key K, therefore resulting in a mismatch. Continuing the probe, K hits on the low-high range of the orange node, meaning we can now retrieve this orange node from the cache and possibly short-circuit from here. Similarly, the green low-high also hits in the cache, serving as a possible short-circuiting node. When there are multiple possible nodes to short-circuit from, we pick the node lower down in the index, making the short-circuiting highly effective. There are more details in the paper on how we handle arbitrary ranges, banks, and sets for the index cache. If no matching ranges are found in the index cache, it is considered a miss. In such cases, the lookup starts from the root and queues up possible nodes to cache while descending down the index. Say there is a future walk that goes to the same leaf node, then we had to cache the green node previously. Now consider another walk that goes to a different leaf node, but however traverses the same orange node. Then we had to cache the orange node previously. We introduce reuse patterns to make this decision by looking into walk cooperation. Metal proposes two contributions. The first
Reuse patterns establish locality within an index by looking at key data, diverging from an address-based locality such as temporal and spatial. Pattern descriptors concisely define index features and can be viewed as flags which can be easily set to pinpoint caching. The algorithm expert selects from index features in the descriptor, and Metal monitors compute access patterns to determine what to cache. Here, it's the orange level. The descriptor chooses entries to cache during a walk. The blue rabbit triggers an insertion at the orange level. This way, Metal enables future traversals to be short-circuited. Reuse patterns help to manage trade-off between two competing concepts, that is reach and effectiveness. We identify three reuse patterns that cover the entire application space. The first being the level reuse pattern, which sets levels to cache in an index. Second is the branch reuse pattern, which sets the fan out and depth to the cache, starting from a key value. Finally, the node reuse pattern, which sets the exact node to be cached. The descriptor is selected at the beginning of an application and remains fixed thereafter. However, a statically chosen descriptor can dynamically focus on key regions. Building on previous example, we see that one of the walk moves to a new sub-branch guided by a descriptor. This altered traversal opts to include the new orange node, showcasing Metal's implementation of dynamic capture. We integrated Metal onto state-of-the-art spatial architectures and evaluated it across benchmarks ranging from database scans and to PageRank. Here, we show the performance plot where the x-axis shows the overall speed up normalized to a baseline streaming approach. The y-axis shows that, and y-axis shows us, x-axis shows the subset of workloads we have benchmarked. Metal outperforms the address cache by 4 times, which can be attributed to the two major benefits. First, we reduce the walk latency by short-circuiting, and secondly, we reduce the working set. We also make a comparison of Metal with specialized DSA cache, the X cache, which chooses to cache the leaf nodes as they are closest to data. On the other hand, Metal is able to dynamically choose what to cache. Xcache is unable to reduce the working set, therefore thrashing the cache. Hence, Metal is able to outperform Xcache by 2.4 times. Let's focus on why caching the leaves isn't a good idea by looking at two contending workloads. Sets is an ordered hash table workload, which can be viewed as an n-level deep tree. Here, we capture node reuse, but the performance gain is limited due to the target cache region being larger. On the contrary, the scan workload uses a level reuse pattern, which has a smaller cache region. Let's look at how Metal scales. The x-axis shows us the size of the index cache, and the y-axis gives us speedup normalized to an 8 KB index cache. The target hardware is a 128-tile database accelerator. We see that scaling the index cache size to 16 KB barely increases performance as the workload is bandwidth limited due to unidentified reuse. We suddenly see a spike in the performance at 64 KB. This is attributed to the effectiveness of the cache. And finally, we see that the performance gains of Metal is parallelism limited, since we demonstrate a single index cache shared across all tiles, which is causing a cap on the total performance. In conclusion, we open the floor for more discussion to be had about adding another cache targeted to optimize index data structure. We present a novel caching framework, which is easily portable across various state-of-the-art spatial DSAs. And Metal urges the community to rethink how to capture locality in sparse compute workloads. Thank you.
Interesting thought. There's a lot of analogy between this and page table walks, right? I mean, multi-level page tables, right? Have you thought about either applying this idea there or some of the ideas there where the indexes are not sparse but more contiguous and so on? Have you thought of exploring that synergy for address translation or vice versa?
One of the main comparison points when we were actually building this model was that it always came down to the point that it is very similar to a page table. So we wanted to kind of bring that distinction because when it comes to page table, you kind of have to have the whole path cached. So you need the prefix trees complete path to be cached. Here, you are actually capturing a single unique node, which is like short circuiting.
I understand, but the page table, actually at the end of it, you're just worried about the last level, right?
Yes.
So if we can do that mapping from the original to the last level, which is what the eventually TLB is containing.
Yeah.
If you have a structure like a TLB for this, add it on, would it help?
Maybe. I'm not. Yeah.
All right, next speaker. So our second talk is GMT, a GPU orchestrated memory theory for data era. And Chia-Hao is going to present the paper.
Okay, thank you. Hello, I'm Chia-Hao. I'm from Penn State. So I'm glad to be here to present our paper. Mike? No. Okay. So I'm glad to be here to present our papers, GMT, GPU orchestrated memory theory for the big data era. And a special thanks to our collaborators from NVIDIA. Without their contributions, this work could not have been completed. So GPUs have been widely used to accelerate applications in many areas, such as machine learning, data analytics, and so on. However, with data demands in applications growing at a much faster rate than the increase in GPU memory capacity, we are encountering a bottleneck known as GPU memory wall. The issues not only have long latency, insufficient bandwidth, but also limited capacity. Due to limited capacity, the GPUs cannot accommodate the entire working set. So typically, GPU programmers need to explicitly copy portions of data from the CPU memory to GPU memory to enable access by GPU threads. The amount of data that can be moved is limited by GPU memory capacity, making this approach unsuitable for applications where threads require access to the entire data set. To break the limitation of memory capacity, traditional solutions such as Unified Virtual Memory or UVM developed by NVIDIA expand the space by including CPU memory. It uses demand paging to move pages between the GPU memory and the CPU memory. However, as data demands keep increasing, CPU memory is no longer sufficient to store all the data. The solution is still limited by CPU memory capacity. To enhance the capacity further, subsequent efforts like Dragon at NGMM extend UVM capabilities, allowing for page transfers between GPU memory, CPU memory, and the storage devices, establishing a three-tier memory hierarchy. Similar to UVM, the whole CPU performs page management and orchestrate page movements between the tiers. While addressing the capacity problem, this method orchestrated by the CPU is inefficient due to significant software overheads and limited parallelism, as pointed out by many prior works. To address the inefficiency due to CPU orchestration, one prior work, Ben, published in ASPLOS 2023, propose a GPU-orchestrated high-throughput system architecture. Its coordinate page transfers directly through GPU and optimize the design through the use of software cache and concurrent queues. However, it overlooks the potential utilization of CPU memory, which could significantly reduce latency if we place data appropriately. To combine the merits of two types of solutions, we introduce GMT, GPU Orchestrated Memory Tiering, which leverages host memory as a tier 2 layer in the memory hierarchy and manages the data pages across the tiers using the GPU. And GMT resolves two important issues. First, after including the CPU memory, we need a smart page placement policy to determine what to place in each tier. Second, we need a mechanism to determine transfer ways to perform efficient page transfers between the tiers. Since we implemented the solution fully in the GPU, let us look at what GPU threads would do. When the GPU thread accesses data, it checks if the corresponding page is in the GPU memory or not. If yes, just return the data byte. If not, it's request the space from the GPU memory for the defaulted page and transfer that page either from tier 2 memory or tier 3 memory. And if tier 1 memory is full, we need to effect a victim page from the GPU memory. Upon eviction, we need to select a memory tier to place the victim page to GPU memory, CPU memory, or SSD. The key to build GMT is to figure out what to do in these two boxes, page placement and page transfer. And let's look at how GMT does page placement. We propose to place the victim page based on its reuse level, determined by the reuse distance or lapiladi. So if it is high reuse, we retain it in the GPU memory. If it's mere reuse, we place it in the CPU memory. Otherwise, we place it in the SSD. We anticipate that each tier can accommodate varying degrees of locality and preserve valuable data pages to reduce the need for accessing lower tiers frequently. So we all know reuse distance refers to the number of unique pages accessed between two successive references to the same page. We all know that it is hard to estimate reuse distance at runtime, so we need a proxy that can be easily obtained. Inspired by prior works, we choose to use virtual timestamp distance, or VTD, as the proxy of reuse distance. VTD can be thought as non-unique reuse distance, the number of non-unique pages accessed between two references to the same page. For instance, in the graph below, we see that reuse distance between the second and the third P1 access is 2. And its VTD is 6 because we count every page access even though they are not unique. The reason why we use VTD is because it's easier to measure at runtime, and we only need to maintain software counter that is incremented upon every collapsed page access. And we store this counter value for each page when it is accessed for future VTD calculation. By dumping memory access traces, we find the relationship between VTD and RD reuse distance is almost linear. We can express this relationship as a linear equation. Reuse distance equals to a slope times VTD plus an offset. We sample VTDs and RDs in the early execution of applications and run linear regression on those samples to estimate the parameters of this equation. So far, we can utilize VTD and the estimated relationship to get reuse distance of the past. But what we really need is future reuse distance so that we can know where to place the page. Remember that we only place pages in other tiers upon their evictions. For example, if we try to page P1 at this point, what we want to know is the future distance between the eviction and the P1's future re-reference. By this distance, we can know how soon this page will be re-accessed after the eviction in the future. We call this distance as remaining reuse distance, or RD, the distance between the eviction and the future reference. After obtaining the RD, we determine its reuse level by comparing it with the capacities of tier 1 and the tier 2. And we can convert the virtual timestamp distance between the eviction and the re-reference called RVTD to RD using the estimated linear equation. Every time when a page is re-referenced after its eviction, we can get the most recent RD to train our proposed tier predictor for future page placement. We again use the memory traces to calculate all the RDs and plot them for the applications. In our findings, certain pages RD consistently remain similar across every eviction, while others exhibit alternating patterns. This result showed RD and its corresponding tier has good predictability, and we can use the past RD to predict future RD. We take advantage of this characteristic and then propose a predictor to predict future RD and its corresponding tier. This answers the initial question we asked earlier, what tier to place for the victim page. Because of the time, I will not go through the details. Please refer to the paper for the details, or we can chat about it further after the presentation if you are interested. Now, let us go to the other question. What ways to use for page transfers in GMT? Basically, we want to optimize page transfers between the tiers. For GPU memory SSD transfers, we use BAN, performing direct I/O from the GPU. GPU threads can directly submit NVMe commands to submission queues and to ask for pages and do polling and wait for completions. For GPU CPU memory transfers, there are two ways. We can either use DMA or zero copy that is done by load store instructions. From the right graph, we see that zero copy achieves better throughputs compared to DMA when there's higher demand for concurrent page transfers. However, when the number of pages to be moved is low, DMA emerges as the preferable option. Therefore, we use a hybrid approach to select the optimal transfer method based on the number of concurrent requests. Also, to mitigate divergence impacts, we exclusively use 4 WAPs for zero copy operations. So we build 3-tier GMT on top of BAN, the state-of-the-art 2-tier GPU orchestrated system. We run experiments in a real platform with an A100 GPU and with widely used applications. We also compare our reuse-based policy with other 2 policies, tier order, placing pages following the tier order, and the random policy, placing pages in the lower tiers in a random way. These are the results of speed up and I/O reduction compared to BAN, which is the baseline that does not utilize CPU memory. From the speed up graph, we can see that GMT with all 3 policies can outperform BAN. Even if we randomly place pages in the tiers, we can still get 24% speed up on average. However, if we exploit reuse distance to do the placement, the performance can be improved further to 50%. This can be confirmed by the results of I/O reduction. GMT with the reuse-based policy can achieve 42% reduction in I/O activities, the highest among the 3 policies. It clearly indicates that reuse-based policy surpasses the other 2 policies in page placement effectiveness. The results not only reaffirm the importance of incorporating CPU memory, but also emphasize the significance of placing pages based on their locality. To know why our reuse-based policy outperforms, we check the prediction accuracy. We can see that about 2/3 of the applications can achieve around 90% prediction accuracy. Only when application has very low reuse, the predictor performs poorly because it has not enough history to train the prediction. Lastly, we compare our solution to the state-of-the-art CPU orchestrated system, HMM in Linux. Ours can outperform HMM by over 300%. The result aligns with observations from many prior works, indicating CPU orchestrated approach incurs higher overheads in page management and has limited parallelism for handling concurrent requests. This underscores the advantage of the GPU orchestrated approach over the CPU orchestrated one. To conclude, we design and implement 3-tier GPU orchestrated memory tiering and demonstrate GMT can outperform the state-of-the-art 2-tier GPU orchestrated BAN and 3-tier CPU orchestrated HMM. We propose a discretionary reuse-based page placement algorithm using lightweight reuse distance estimation and tier prediction to approximate the optimal policy for tiered GPU memory systems. We also use a hybrid scheme, exploiting both DMA and zero copy for efficient page transfers. Thank you for your attention. Any questions?
So what's the excess granularity for the pages?
Yeah. So 64 KB. So it aligns with the granularity used in UVM.
Okay, so even for like graph workloads, you're using the same granularity? Because
You mean
this might
IO
be-
application? IO amplification thing?
Yes. So even for graph workloads,
Yeah,
is it
so
the same granularity? So how much is the IO amplification from that?
yeah, for graph application, I believe there's IO amplifications. I don't measure, but for band, they just reduce the granularity to to reduce that effect. But we want to build a generic runtime system and aligned with UVM, so that's why we use that size. Yeah,
Got
but
it.
yeah, for sure, like for graph, there's IO amplification.
And even with that, it's outperforming BAM. Is that
Yeah, because we include
Okay,
like another
even
tier
with
that
that.
can reduce latency.
all right?
Yes.
Thanks.
So your assumption is that the CPU and GPU are separate system, right? So what if for the system like NVIDIA's Grace Hopper, they have CPU and GPU integrate together, or like AMD's APU, the CPU and GPU put together? So would that?
Yeah, we don't have any CPU computation here because we only like exploit CPU memory only, but that CPU memory can be replaced with other memory technologies like NVM or CXL memory. So it doesn't have any like CPU computation here. But maybe in the future we can explore that way. Yeah, thank you.
In the section is GMLake, efficient and transparent CPU memory defragmentation for large-scale DNN training with virtual memory. And we have Jae from the Shanghai Jihoon University presenting the paper.
Hello everyone, I'm Xu from Shanghai Jihoon University. Today I'll be discussing GMLake, a transparent and efficient GPU memory defragmentation technique designed for large-scale DNA training. Firstly, I will talk about our background and motivation. As we all know, large language model has gained considerable popularity. However, the rapid growth in the size of large language model poses a significant challenge to GPU memory. This picture illustrates that while the transformer size increased by 400 times every 2 years, AI hardware memory only increased by 2 times every 2 years. This contrast shows critical importance of GPU memory and highlights the pressing need to overcome the memory war. To address this challenge, various training techniques and infrastructures have been proposed. Among these, GMLake focuses on optimizing the caching allocator at the deep learning framework level. As depicted in the figure on the right, memory allocations in deep learning workloads are both extensive and chronological, adhering to specific memory patterns. The caching allocator effectively manages these allocations through caching mechanism. Despite having a native allocator implementation that allocates device memory on demand and frees immediately after the program execution, this approach leads to massive device-level memory allocations and overhead. In contrast, the caching allocator aims to reduce memory allocation overhead by caching unused memory blocks and attempting to reuse them when possible. Our data indicates that the caching allocator achieves more than 5 times higher throughput on deep speed fine-tuning workloads compared to a native one. Moreover, we have observed that the memory efficient optimizations such as activation recomputations or alpha short result in uneven memory patterns compared to vanilla workloads, as you can see from the right figure, because of the scheduled computation and data transfer. We define the cached memory as reserved memory and the memory currently in use as active memory. Memory utilization is calculated by dividing the size of active memory by reserved memory. Our evaluation has explored that the impact of distributed device numbers and various strategy combinations on memory utilization. Our finding indicates that as we increase the device numbers and implement more memory efficient optimizations, we observe increased fragmentation in the caching allocator due to the uneven memory access patterns mentioned earlier. Let's take a look at what's happening inside the caching allocator. To serve the upcoming request, it splits the cached block into block 5 and block 4, which can cause issues when handling the next allocation because block 2 and block 5 cannot be stitched together. This situation occurs more frequently under memory efficient optimizations contributing to the fragmentations of caching allocator. However, by employing virtual memory stitching operations, we can mitigate this fragmentation. NVIDIA Virtual Memory Management, or VMM in short, helps in constructing VM stitching mechanism. We can firstly create a lot of fine-grained memory chunks and then reserve a virtual memory address. At last, map the address with the created memory chunks and validate the address. We can furthermore build stitching mechanism on the basis of the APIs to stitch multiple virtual memory addresses together. However, this implementation suffers up to 115 times higher overhead when allocating 2 GB memory at 2 MB granularity from the device. GMLake aims to leverage the benefits of virtual memory APIs while mitigating the associated overhead. Now let's dive into the implementation of GMLake and explore the method used to amortize this overhead. GMLake extends PyTorch CUDA caching allocator with our virtual memory stitching APIs, efficient stitching data structures, and NVIDIA's low-level memory management APIs. For example, we have extended the stitch operation in allocation and upstitch operation in deallocation. Additionally, we have constructed a multi-level memory pool to support efficient stitching operations and ensure the correctness. Given an allocation request size, GMLake searches for the proper block in a set descending order from the sorted multi-level memory pool. For brevity, we can summarize GMLake's allocation strategies into 4 scenarios. First, if the allocation size exactly matches the block size in one of the multi-level memory pools, we return a block for the user to use. In scenario 2, if the allocation size is smaller than the primitive blocks, we follow the best fit algorithm and split the block if possible. In scenario 3, when there are only primitive blocks smaller than the allocation size, we try to stitch them together following a certain policy and record the stitched block. In scenario 4, if the total size of primitive blocks is less than the allocation size, GMLake tries to fill the insufficient part with freshly allocated memory, then performs a stitching operation to serve the allocation request. At last, if no memory is valuable, an auto memory exception will occur. It's important to note that the stitched block will be recorded in the stitched memory pool and can be further reused if all the blocks consisting of it are valuable. In short, each stitched block will be used multiple times in the future. That's why GMLake can amortize the VMM overhead. For more details, please refer to our paper. Let's consider an example. There are a series of memory requests from request 1 to request 6. In the original memory pool, request 1 and request 2 will be served with newly allocated memory blocks 1 and 2, due to their left circle overlap. Request 3 will also be served with a newly allocated memory block, because there are no larger blocks to perform the best fit algorithm. This pattern repeats with request 4 and request 6. However, request 5 can reuse the cached block. GMLake handles this allocation as follows. Request 1 and 2 are served with the same behavior as the original allocator following a scenario 1. Request 3 is served with a stitch block according to scenario 2. Request 4 and request 6 reuse valuable blocks and fill the insufficient part with freshly allocated block. In conclusion, GMLake optimizes memory consumption and amortize stitching overhead by appropriately reusing cached blocks. At last, we are going to our evaluation section. We conducted our evaluation on 16 NVIDIA A100 GPUs with multiple large language model fine-tuning workloads. In our evaluation of strategy combinations, we achieve an average saving of 10 GB and 17 GB at most. For evaluation of distributed device numbers, we observe an average memory reduction of 8 GB and 17 GB at most. We also conducted evaluations on batch sizes and different training devices. Different training engines, GMLake performed well across all these scenarios, whereas the original PyTorch encountered auto memory exceptions. We have also conducted throughput evaluations. In our evaluations, GMLake's throughput aligned with that of PyTorch. Finally, the memory profile provides valuable insights. As seen in the image, under the same configuration, PyTorch exhibits fast iteration but encounters auto memory issues in the first 4 steps. In contrast, GMLake requires several slower iterations to complete the stitching operations. However, after the initial phase, GMLake offers a stable and efficient training experience. This is because most of the stitching operations are already completed. Let me summarize GMLake. Firstly, we conducted a characterization study revealing significant fragmentation issues with the caching allocator. Secondly, we developed and implemented GMLake, a novel memory allocator designed to effectively reduce fragmentation and enhance memory utilization in large-scale DNA training. Lastly, we extensively evaluated GMLake across multiple prominent large language model optimization platforms using a range of representative open source large language models, showcasing its effectiveness, efficiency, and robustness. Additionally, we have made several updates to our project. For more details, please check it out at our GitHub repo. Thank you.
I had a question. Is there anything specific to GPUs or LLMs for this? I mean, isn't this a general optimization you could do even for CPUs and any kind of workloads?
It's maybe possible if we have built our stitching mechanism on the basis of NVIDIA Virtual Memory API. It provides us with the ability to stitch the virtual memories. If CPU provides that APIs like a VMAP in Linux, we can also
No, but you could take a slab allocator or something like that and do the same thing there as well, right?
Oh, may I have pardon?
No. What I'm saying is even the normal slab allocators that we use, we could have done something very similar there as well, right?
Oh, we are optimized for large scale DNA workload, not a general allocator.
The next talk is from Yuan by Jihoon Chang. He is going to present direct memory translation for workflow.
How is it connected?
Oh, this
one?
Yeah.
Hi everyone, I'm Jihoon from UIUC. Today, I will present our work, Direct Memory Translation for Virtualized Cloud. In this work, I will show you how we build a software hardware extension that minimizes page table work steps while maintaining compatibilities with existing Rex page table designs that are used in many architectures. This is a collaboration between University of Illinois and the University of Rhode Island. Today, the de facto page table design is a radix page table. However, due to the increasing popularity of memory-intensive workloads, such as machine learning workloads and in-memory database workloads, address translation for this design has become a major performance bottleneck of these applications. A key reason behind this is we need 4 or more sequential memory accesses for a single page table work. On the other hand, CPU caches cannot scale at the same pace as the growth of memory capacity and application working size. Therefore, the traditional way of using caches to hide address translation overhead is less effective. In virtualized environments, we use nested translation for address translations, and it is even more expensive. This is because for each guest page table accesses, we need 4 sequential fetches in the host page table to locate the page table entry in a guest page table, resulting in a 2-dimensional page walk with 24 sequential memory accesses. If we use 5-level page tables, the sequential access count will become even higher. On the other hand, though caching can save a lot of latency, they are still costly to access. In our evaluation, we found that the 22 page table entry fetches that shows high cache hit rate still contributes about 30% of page walk latency in our Redis workload. For this reason, we must minimize the steps in translation for low overhead translation. To this end, we must resync virtual memory translation. Our paper presents the direct memory translation, or DMT in short. It is a software hardware extension that shortcuts page table walks down to 1 for native case, 2 for virtualized case, and 3 for nested virtualized case, which was untenable due to the excessive page walk count. DMT directly fetches the last level page table entries that are the PTEs that contains the mapping information of virtual addresses to physical addresses. And the DMT is fully compatible with existing Redis page table designs, such as those used in x86 and ARM. It is flexible and scalable for real-world implementation, and it speeds up page table walks in a virtualized environment by an average of 1.58 times, resulting in a 1.20 times speed up of application execution. Our key idea is to build direct mappings from a page to its last level PTE, so that for the nth page in a virtual memory area, which are the in-use contiguous memory regions in a virtual address space, DMT places its translation into the nth PTE in a translation entry area, which is a physically contiguous region that we built to contain the last level PTE. DMT fetches the target PTE use direct mappings during page walk. DMT first finds the page number of a page in its VMA, and then it uses the page number to access the corresponding TEA to locate the PTE and fetch it and do translation. DMT is compatible with existing Redis page table design that are used in many architectures, as it only changes the memory layout of the last level PTEs. The system may still build Redis page table and work the tree at will. Either work via the DMT or the Redis tree, the translation result will be the same, as the same last level entry will be accessed. DMT requires minimal hardware support. On the software visible side, DMT exposes TA registers in the instruction set architectures that are side by side with the existing Redis root, such as CL3 or FTR. Each TA register contains the base address of a VMA and its length, as well as the root address of a TA. On the implementation side, DMT adds a PTE fetcher side by side with the existing Redis page walker in the macro architecture, so that if TA register is properly set up, the DMT fetcher can directly fetch the last level entry, or otherwise, it will automatically fall back to the Redis page table walker to guarantee a correct translation. Because application has sparse memory layout, DMT also supports multiple direct mappings via multiple TA registers. DMT checks the belonging of the translation virtual address to decide which mapping to use, so that only one memory access will be issued on the correct TA. DMT also merges mappings for better coverage because there are only a limited number of registers. DMT do this by merging adjacent mappings with small holes, and our test show that 60 direct mappings can cover 99% of application working set in all the 84 applications we have tested. DMT supports huge pages and transparent huge pages for parallel lookup. It built individual TEAs for different page sizes. For example, the 4K TEA and 2 MB TEA, both are mapped to the same virtual memory area. During translation, DMT parallelly look up these TEAs to support mixed page size VMAs, as seen when using transparent huge pages. DMT also prefers to shortcut the largest mappings if the count of VMA is larger than the count of available registers. This is because the largest mappings usually experience high page walk overhead, and they are used to store application heaps and application data. DMT will fall back to Redis page walk for inactive direct mappings. DMT naturally scales to virtualized environment. So in a virtualized setup, the guest OS uses guest TAs to map guest virtual address to guest physical address for a single application. And the host OS uses host TAs to virtualize guest physical address from host physical address for an entire virtual machine. To translate a guest virtual address to guest physical address, DMT needs to read the guest PTE. And because it has an unknown host physical address location, DMT needs to first find the physical location of the guest PTE via the host TEA. And then, with the translation information in hand, the translation can be done. To translate a guest physical address to host physical address, DMT reads the host PTE again to do the translation. In the end, DMT used 3 accesses to perform a single nicety translation. But we can further apply DMT's insight for parameterization optimization to further reduce the nicety walk access count. DMT can optionally build guest virtual address to host physical address direct mappings to directly locate the guest PTE, so that no host TEA access is required to fetch the guest translation information. And then, with a second access, we can do the translation. This scheme scales to nested virtualization. So DMT always builds direct mappings to the machine physical address space. And DMT, to our best knowledge, is the first translation scheme that supports nested translation. In contrast with vanilla Radix design or optimized DMT, which works goes equationally with a number of nesting depths, the optimized DMT shows a good property that its translation gap count scales linearly with the depth of nesting virtualization, or the count of address spaces need to be traversed. To assess the effectiveness of DMT, we use a memory hierarchy simulator called Dynamo.io to simulate the hardware. We collect memory traces from various workloads using different areas such as machine learning, in-memory database, and physical simulation. We have our artifact open sourced. We have done extensive evaluation in native, virtualized, and nested virtualized setup. Here we show the result for our virtualized setup as it is the main result. This figure shows the relative page walk speed up against vanilla KVM x86. We show the result for individual workloads and also the geometric mean. We evaluated DMT against 4 state of art, including flattened page table, elastic cuckoo page table, agile paging, and prefetched address translation. We show the result for unoptimized DMT, as well as the paravirtualized optimized DMT. The results show that DMT achieved the largest speedup in page walk in all workloads, as it requires the minimal amount of page walk accesses. This in turn leads to a substantial speedup in application execution speedup. Since DMT requires no expensive software operations, it shows low overhead in. To summarize the evaluation results, DMT speed up page walk by an average of 1.28 times over vanilla x86 in a native case and 1.58 times in virtualized case. This speed up application execution by an average of 1.05 times for native case, 1.20 times for virtualized case. And for nested virtualized case, because DMT removes the shadow paging overhead as it enables hardware 3-dimensional work, it shows a 1.48 times speed up over vanilla Linux in this nested scenario setup. In conclusion, DMT is a software hardware extension that minimizes the page walk access count while maintaining full compatibility with the existing Radix page table design. It shows promising speed up in both page walk and application execution, and it is flexible and scalable for real-world implementation. Thank you for listening. I can now take questions.
The virtualized field is needed one at the top. If you are the shadow mode and to look up on mode if you are in the perspective. So to compare that to your case where you want to look up, in which cases do you think agile trading more mainstream works, and in which cases you are
That's a good question, but I want to correct that is because agile paging does not change the hardware translation scheme. It still requires 4 sequential accesses in a shadow page table work mode. and at most 22-fold if we use nested work.
Hi, Chris Rosbeck, UT Austin. Haven't read it, so I probably missed something important, but are you requiring physical contiguity for every VMA
Yes.
for this to work? And if
Yes.
so, how realistic is that?
So a typical volume for a 100 gigabyte VMA, it will require 200 megabytes of contiguous TEAs. But because this thing can be flexible, we can actually split a TEA in half if the contiguity is not enough in the machine. So you can use 2 TEAs to map a same VMA and each responsible for a different area.
Have you studied your system after a system gets pretty fragmented yet?
Excuse me.
Have you studied the system in a fragmented state?
Yeah. So yeah, we will use the Linux default contiguous memory allocator, and it will automatically defragment the memory when necessary.
Okay, thank you.
The last documentation was also available for education page tables for human searches. And we have they've been used from the Chinese Academy of Science.
Okay.
So it doesn't work. This one. Still doesn't work. Okay. Yeah. Okay. This is a mine. Yeah. Is it working?
Yeah, just
Okay. So then I frame it. Yes. Yeah.
no more daily.
Good morning, everyone. I'm very sorry for wasting 2 minutes. Yeah, I'm Jihoon from Chinese Academy of Science. So today I will talk about WASP, workload-aware self-replication page tables for NUMA servers. So this is the agenda I will talk for today. And so firstly, I will talk about the background. So NUMA is the standard architecture for servers nowadays. So traditionally, the user space data may located at multiple NUMA nodes. Remote access will take 2 to 4 times longer than the local access. So we call this is a data page cost NUMA effect. So actually, there is a lot of research or studies to try to reduce the data page cost NUMA effect. Auto NUMA is one example for this purpose. But also for the kernel space data structures, like the page tables also may locate at the multiple NUMA nodes. And the remote access will take 2 to 4 times longer than the local access. But nowadays, you know, the workloads consumes much more memory than before that workloads. So in this case, for example, and one workload may use several hundred gigabytes. So in this case, the page table cost Newman effect is getting more important. So we can also see the page table cost Newman effect is equally important to data page cost Newman effect. Okay, so this is the situation. So actually, currently there are some solutions to reduce the data page table cost Newman effect. So actually, the one work is so-called mitosis is also in ASPLOS'24. And the key idea of the mitosis, they use the page table self-replication, and we call it the PTSR. And you can see the PTSR indeed can improve the performance of the programs, but for different programs, they improve different performance, and up to the 1.74 times. However, we find that there are some problems of a current PTSR solution, and we can see PTR may improve or hurt the performance of application. And we can see, I do the experiments in two cases, and you can see from the left figure, we can see, and if we enable the PTSR, like the lowercase r denoted, and it can almost reduce the page table cost Newman effect. But on the right figure, you can see when we enable the PTSR, it does not reduce the Newman effect. It's worse. It can degrade the performance more. So this is currently the phenomena we observed for the PTSR. But why? The reason is a lot of reasons for there. And the reason is because sometimes there is some contention on the Newman nodes. If there is some contention, we can see the local access is not always the best. So in this case, current PTR solution does not consider this situation. This is one shortcoming of current solution. The second one is that the current PTSR need users to manually enable it or disable it. But this is very difficult for users to know. So what we want to do is we want to have an automatic solution for the page table cost Newman effect to reduce it. So to do that, so firstly, we need to characterize the PTSR for the different programs. So we characterize in two scenarios. So firstly, we call it a multi-socket workloads. So this means the workloads will use multiple Newman nodes when it ran or when you deploy the workload. The second scenario is it is a common solution phenomenon because in current OS it will for the balance load balance it will move your thread from one Newman node to another Newman node from time to time. So these two scenarios. So let's look at the first scenario. We can see for the first scenario, we see we also need to consider different memory allocation policy. So here we consider two policies. First, the so-called the first touch. Secondly is interleave. So for the first touch, we can see this is how the page tables distributed into the different Newman nodes. So we can see the first touch is significantly skews the distribution of the page tables. But for interleave, you can see it's evenly distributes the page tables. So in the two different cases, so the PTSR will have different effects for that. And also, I give an example here for Canal. We can see, and we have different levels of the page tables. So we can see the PGD is the global directory. So if PGD is here, so we can determine that this workload is launched at the node is first launched at the node 2. Yeah. So this is a distribution for the multi-socket. So there's some skew for that. For the migration, you can see, and after we do the migration, so we can see the PTSR significantly affect the performance. But for different programs, they have different effects. So this is the first characterization for that. Second, we can also, we look at some different characters. You can see the LAR, so-called local access rates. And we see the INI, this so-called interconnection imbalance. So we look at this metric. And MCI is so-called a memory controller imbalance. So why we look at this metrics? Because in a standard or in a typical servers, there are many, there are several memory controllers, or in the connection, we have a number of links. So we look at the memory access of different memory controllers, and we see how the attributes of the memory access. So we can see the left figure and the right figure. And what I want to show you that, so you see if the PTSR improve the performance, the MSI, that is the memory controller imbalance, were decreased, but the interconnection imbalance also decreased. So this is we reflect the PTRs can improve the performance. But if the PTRs are reduce the performance, and we can see we can see the right figure. The MCI, you can see it's increased the memory imbalance, but also increased the interconnection imbalance. So when we design our solution for that, we need to consider and these factors in our solution. So this is the characterization. And so after we characterize it, so we want to propose our WASP methodology to automatically reduce the page table cost Neumann effect. So we look at, so firstly, we need to have a set of indicators to indicate whether we should enable or disable the PTSR. So actually you see the indicators we used to indicate if PTSR should enable or disable. So this is the first purpose. Second is we need to use it to enable which page table replica to use. And nowadays already showed. So for the local replica or remote replica, we need to use data indicators to determine. And third is the indicators should be generally available on most processors. Yeah, so if we depend on some specific process indicators, maybe it works on some processors, but not work on other processors. That is not the solution we want. So, okay, so this is the requirement for the indicators. And then we identify, through the previous indication, we identify 3 indicators. First is, we call it MAR, is the memory access rate, just to indicate whether this program is memory intensive or not. If it is not in the memory intensive, so PTSR will not have any benefits. Second is DTLB miss rate. Yeah. And the third one, we call it the page table access latency. Actually, you can use it, data page access latency still works. And this is the general indicators, and this is the implementation on the ARM processors. So in the ARM, we have a performance counter, so-called memory access, and T is the time we counted the memory access. And DTLB, and this is we use DTLB walk and the L1 DTLB is 2 performance counters. And for the PTL, we use the actually is a program and latency memory reading in LM bench to measure the memory access. Yeah, so this is for ARM, but we also implemented on x86 processors. And we can see x86 we use the memory node and the memory store. So these are very common performance counters on the x86 processors. And for the DTLB is a little bit complicated, so we use the these processors. I don't want to just describe it. And also for the PTL, we use the same. Okay. And next, so after we have these indicators, and then we design a mechanism to automate the PTSR. Okay, so actually, we call it, it is a gradual and hierarchy and gradual mechanism for that. So first it is, and here we can see we determine if an application is a memory intensive. And if it is a memory intensive, then we determine the DTLP miss rate is high or not. So we will set a threshold. If it's larger than the threshold, and we will go to enable the PTSR. And then in the step 4, we will determine whether the local memory access is longer than the remote one, and determine we should use local replica or remote replica. And here is the how to say, this is the algorithm we use to determine the automation of PTSR. Okay, and then after we have this methodology, we develop something, some approaches to applying the WASP on an application. So this is the procedure. I don't want to describe all of them. I just want to mention 2 important things. Firstly, with the performance event open, we modify this call and to observe the performance contours in very low overhead. And then we develop a syscall. So for the PTSR syscall, use this syscall and to enable the PTSR or disable it automatically. Okay, and so next we will see the results. And we use 2 different platforms. And the first is ARM server, and this ARM server is a 4 neural node, and the X80 server is 2 neural node. And we also implement the WASP into 2 Linux versions, and this is the Linux kernels, and this is the workloads we work in. And so this is the result, and we can see for interleave the improvement is not that much, but for the first touch it improves a lot. And you can see this is for 4 page tables, 4 key kilobyte page tables. This for 2 megabyte page tables. You can see this is the improvements. It's a lot, and we also tried on x86. This 86 also 16% improvement. And we also evaluated on the, we also investigated why the 4 neural nodes improves more than the 2 neural nodes. Yeah, just because there's some, how to say, if 4 neural nodes, there's a higher possibility for the page tables located on the remote neural nodes. Yeah, and also you can see all these approaches can achieve at least the similar in performance improvement as the manual solution. But because we determine whether local or remote is the best, so we can see the WASP can improves more than the manual approach. Yeah, one thing we need to point out that WASP currently does not coordinate well with AutoNuma. That's for data page tables. But this in our future work, we will develop some approaches to coordinate them well. Okay, and next, finally, I'll give the summary. First, we see it's an automatic approach used to reduce the page table cost NUMA effects. And WASP achieves at least the performance improvements brought by the manually enabling or disabling PTSR approach. And in some cases, WASP improves more performance than the PTSR significantly. And also we implement this in ARM and x86. And that's it. Now it's I'm happy to take questions.
Joseph Torrellas, Illinois. Just a simple question.
Yeah.
Have you found cases when the memory access rate is low?
W access rate
is low, right? And it's best not to enable PTSR.
Yes, in some cases, but in some few cases, we indeed notice that. Yeah, not enable it. Maybe the performance is good, is better. Yeah, we find something.
Okay.
Yeah. That why we this, because you see sometimes your program brings up one human node, but there's another human node application, co-location.
That's right.
They will contain
Yeah.
the memory controllers, or they will contain the NICs. Yeah, so in this case,
And-
enable the PTSR, the performance will get low.
And what about the updates of the things? If it's replicated, you need some overhead potential, right?
You update the page tables, right? Yeah, this also could will incur some page overhead. Yes. Yeah.
So it sort of follows up on what Josepa asked. Based on, I mean, this almost seems like a black box. You know, I monitor some metrics, and based on that, I move things around and so on.
Yes.
If I want to get some intuitive feel out of this to figure out, oops. If I want to get some intuitive feel for, you know, what kinds of page table entries need replication. I mean, there is a sweet spot, right? I mean, there is a TLB, there is a cache,
Yes.
and this replication is going beyond that to sort of move across my NUMA nodes and so on, right? Is there a sense of...
Actually, we look at more than 10 metrics at the beginning of this work, and then we determine we use the 3.
No, I understand. But if I want to, you know, at some point, let's say programmers or compilers or things like that are even going to direct what kinds of entries should be replicated and so on, right? Is there a sense that we can get of, you know, not the entire page tables, you know, only this layer or this cluster of page table entries and so on, right? Can we get a sense of that based on the, you know, extensive experiments that you've done?
I'm not sure the very accurate sense, but I can see, you'll see the figure we see. And in some cases, when you replicate the data, it will improve the memory consumption a little bit, and also increase the traffic between the memory controllers. So if you increase the memory traffic a lot, it may make the local access longer than before. So we need to look at that.
So the other way of asking the question is, this can be done only at runtime? I mean, there is no way of figuring out.
You mean compiler time?
I'm just posing the
Okay,
question.
maybe we can try, but I don't try that. Yeah. Okay.
The session will start at 11:40.